Hello everyone. In the last class, we started our journey into seismic design of masonry buildings. We have looked into various material specifications related to masonry unit, mortar and steel reinforcement. In today's class, we will take our discussion forward and look into various geometrical detailing of masonry walls as well as lateral supports needed by these walls. To begin our understanding of various geometrical details of masonry walls, we will first look into effective height, effective length and effective thickness of masonry walls. When we are looking into effective height, of masonry walls, we have few classifications. It depends upon the supports at the two ends. Now, the support can be full or partial. By partial support, I mean that we will have support only in the lateral direction, which means it does not allow the lateral translation of the wall at that point. But a full restraint will mean that apart from restricting the lateral translation, it will also restrict the rotational movement at that point. So, if you have a full restraint at both the ends of a masonry wall, that is, the wall is not able to have lateral translation as well as rotational movement at both the ends, then we have the effective height as 75% of the height. What is H over here? H is the height of wall between the supports measured center to center in case of RC or timber floors. If you are doing the measurement for H when you have footing at the bottom, then in that case H is measured from the top of the footing and not from the center of the footing. Alright, then if we have the full restraint at one end and partial restraint at the other end, then the effective height shall be equal to 85% of H. Now, when can this situation arise? Let us say if you have a reinforced concrete slab spanning on the wall with adequate bearing or anchoring at one end, that will give you a full restraint at that end, but at the other end you have a timber floor which is not spanning on the wall or not adequately anchored at the other end, then in that case we say that to be a partial restraint at the other end, and that is why you will have effective height of 0.85 H. Now, if you have a partial restraint only lateral at both the ends, then in that case the effective height shall be equal to 1 times of H, that is, it will be the same as the height of the wall. How will you get such a support? If you have a timber floor at both the ends of the wall and that timber floor is not spanning on the wall and it is poorly anchored, but it is adequately anchored, then in that case we call it to be partial restraint. Then you can have a full restraint at bottom and there is no restraint at top. Where will you find such walls? It will be in form of parapet wall at the roof or freestanding compound wall. You can also have retaining wall. So, in those cases you will have the effective height as 1.5 times of the height of the wall. Mostly in case of freestanding wall, you can see that H is measured from the top of the footing. So, this figure has been adapted from IS 1905 and it gives a very systematic definition of these effective height. You will find that various cases have been illustrated through these diagrams, very simple and easy to understand. I suggest that you have a copy of your code IS 1905 ready at your desk while you go through these video lectures. Now, having understood the effective height of masonry walls based on support conditions, we should now understand the effective height of masonry columns. Now, what are masonry columns and how are they different from masonry walls? More or less they are alike. However, it depends on the geometry. If the width of the masonry member exceeds 4 times the thickness, then we call those things to be masonry walls, and if the width or the length of the wall is less than 4 times the thickness, then we call such elements to be masonry columns actually. And in case of masonry columns, it depends on the restraint at the top. If you have full restraint at the top, that is lateral as well as rotational restraint, then you have effective height being defined in different ways for the two direction. For a direction perpendicular to the wall plane, the effective height shall be 0.75 h plus 0.25 h1. H is the same thing, height of the wall between the supports measured center to center. In case of footing, it will be measured from the top of the footing. At the same time, h1 is the height of the taller opening. So mostly for the door among door and windows, you will find that the door is a taller opening. If you are measuring effective height in a direction parallel to the wall plane, you will have the same as the height of the wall between supports measured center to center. Now, if you have a partial restraint at top, that is you have restricted lateral translation at the top, but the wall can generate some rotation at the top, then in that case, for a direction perpendicular to the wall plane, if your height of none of the openings exceeds 0.5 times of the height of the wall, then the effective height shall be defined as the height of the wall itself, because your openings are sufficiently small. If your openings are large, that is the height of the opening, any opening exceeds 0.5 h, then in that case we tell that the wall is not properly bounded in the geometry, and therefore the effective height will increase to 2 times of the height of the wall. And in case of direction parallel to wall plane, any opening shall be able to render the wall to be not bounded sufficiently, and therefore in the direction parallel to wall plane we have the effective height as twice the height of the wall. Now, once we have understood the effective height of masonry walls and columns, now let us try to understand the effective length of masonry walls. How do you obtain the effective length of masonry wall? Again, it depends on the boundary conditions. So here we have shown a few different figures which have been obtained from commentary of IS 1905, which has been drafted by Professor Durgesh C. Rai, and in this case we can see that different boundary conditions lead to different effective length of masonry wall. Let us look into the first case, where you have a wall which is continuous and is supported by cross wall. So these are cross walls. It can also be a pier or a buttress. So this very wall is being supported by these cross walls, and apart from the support, the wall is also continuous, and therefore the effective length of this very wall shall be 80% of the length of the wall. Obviously, in this case the opening has to be a small, that is the opening should have a distance of at least h by 8 from either face of the cross wall. So x should be greater than or equal to h by 8. Similarly, y greater than or equal to h by 6 implies that the cross wall should be functional only if it has a certain length. Okay, now let us look into the second case, where we have similar thing, but at the one end the wall is not continuous like this. Here the wall has stopped at the cross wall. It is still supported by that cross wall. So in this case the effective length shall be 90% of the length of the wall. All these things are obtained from clause 4.4 and table 5 of IS 1905. You can always have a look. I suggest that you keep the copy of the code ready with you, and then in this case the wall is supported by the cross wall or pier or buttress at both the ends, but it is not continuous. So, in this case the effective length shall be equal to the length of the wall. Let us look into this. This case shows us a wall which is having a length L2. We are looking into this wall. So, this wall is free at one end because of the opening, and at the other end the wall is continuous and is supported by the cross wall or pier or buttress. Therefore, it shall be equal to 1.5 times of L2 in this case. So, here we have mentioned that case 1.5 times of the length of the wall. Finally, this case where we have the wall being free at one end, as you can see we are interested in this wall. So, this is free at this end, and at the other end it is supported by cross wall or pier or buttress, and in this case we say that the effective length shall be twice the length of the wall. Now, between these two cases, what is the difference? In this case the wall was continuous over the cross wall or pier or buttress, but here it is only supported. Why we are not considering the continuity in this case? Because the value of x is less than h by 8. So, in such case we say that the wall, this very wall is definitely supported by this cross wall, but it is not continuous. For continuity we need this x to be larger than h by 8. However, not all of these are mentioned in the code IS 1905. However, it has been followed in practice usually. Okay, and if you have openings which are taller than half of the height of the wall, then in that case that end of the wall at the opening shall be assumed to be free. Okay, once we have understood the effective length, now let us look into the effective thickness of masonry walls. Now, we can have two types of walls. One is your solid wall, another is your cavity wall. Why do we construct cavity wall? Usually for good thermal insulation. Now, in case of solid wall, the effective thickness is very simple. You can take it as the thickness of the wall. However, if the solid wall is adequately bounded into pier or buttress, then in that case effective thickness may be taken as larger than the thickness of masonry wall. So, if you have the slenderness ratio based on effective height, for that case it will be a stiffening factor or stiffening coefficient CS multiplied with the thickness of the wall. If your slenderness ratio is based on effective length of the wall, then the solid wall shall still have the effective thickness as the thickness of the wall. Now, as you can see, table 6 from IS 1905 gives us the value of a stiffening coefficient for walls shown as CS over here, and for this value of a stiffening coefficient we need some terms like center to center spacing of the pier or cross wall. We also need width of the pier in the direction of the wall or actual thickness of the cross wall, and based on this you shall be able to obtain the value of stiffening coefficient, that is CS, and this stiffening coefficient, if you closely observe, it is always greater than 1. Why is it so? Because we are considering this stiffening coefficient only for cases where you have the solid walls adequately bonded into piers or buttresses. Then we have cavity walls. In case of cavity walls, the effective thickness will be taken as 2/3 of the sum of the effective thickness of various leaves of the cavity wall. Typically in a cavity wall you have two leaves because you have a hollow space between the two leaves, or sometimes they are also called as widths, and between those two leaves you have some gap for thermal insulation. So, TW1 is the effective thickness of the first leaf of the cavity wall, and TW2 is that for the second leaf. Now, again, since these two leaves comprise of solid walls in their own right, therefore TW1 and TW2 should also be modified based on the stiffening coefficient. using the same table 6. Okay, now once we have understood the effective dimensions, that is effective height, effective length and effective thickness, we can obtain the slenderness ratio. So, we can obtain slenderness ratio of masonry walls or columns in two terms, that is, one is effective height divided by effective thickness, HE upon TE, and the second is effective length divided by effective thickness, which is LE upon TE. We have to consider the maximum of the two based on clause 4.6 of IS 1905. Now, once we have calculated the slenderness ratio, this slenderness ratio shall be checked against some limit. Why do you need such limit? So that you have desired failure in your masonry wall. So, if your masonry wall had number of story 2 or lesser, that is up to 2 story height, then if you have used cement mortar while doing the masonry work, then the maximum slenderness ratio shall be equal to 27. If you are using lime mortar, then your maximum slenderness ratio is 20, lower than that in the case of cement mortar. Why? Typically lime mortar will have much lower strength than cement mortar. Why is it so? Because in lime you rely only on carbonation to get strength. Compared to that, in cement you have the hydration going on. Now, if your building has more than 2 stories, then in that case, if you have used cement mortar, then the maximum slenderness ratio is 27, and if you have used lime mortar, then the maximum slenderness ratio of the wall shall be limited to 13. This is true for walls. In case of masonry columns, recall masonry columns were defined as those masonry elements in which the length to thickness ratio was less than 4. In such case, the slenderness limit is defined as 12, and since masonry columns have the length to thickness ratio of less than 4, so that slenderness ratio defined based on effective length is alright, it is obviously less than 12, but we also need to check the slenderness ratio based on effective height, that is effective height divided by effective thickness. So, that has to be less than 12. Now, once we have understood slenderness ratio, let us also understand eccentricity in masonry buildings. Now, there are a lot of factors that affect eccentricity of the vertical load in case of masonry building. Typically, in a masonry building, you have various load bearing masonry walls comprising of masonry units and mortar, and on those walls you have the slab, which is typically of reinforced concrete, or it can also have a timber flooring placed on that wall over those walls. However, the loading coming from the floors can be eccentric on the wall. It depends on extent of bearing, whether the slab is completely placed over entire wall thickness or not. If it is lesser, then there shall be some eccentricity towards the slab or floor. The magnitude of loads, stiffness of slab or beam, fixity at the support, and construction details at the junction. All of these factors affect your vertical load eccentricity. Further, there are some guidelines given for obtaining eccentricity. These guidelines are given in Appendix A of 1905/1987. However, the assessment is majorly based on judgment of structural engineer. Now, let us look into these guidelines. Let us say that we have a RC slab with a span not exceeding 30 times wall thickness. Such spans are usually called as normal spans because they are ordinary, and in that case, if your slab bears on full width of the wall, then obviously there is no eccentricity, but the slab bearing on partial width of the wall will give you an eccentricity of 1/12 of the wall thickness. Similarly, if your RC slab has a span which is exceeding 30 times wall thickness, which means it is a large size span, and in that case if your RC slab is bearing completely on the full width of the wall, still due to the large span of the slab, you will be left with design eccentricity of 1/6 of wall thickness. And if your bearing is not on the full width of the wall, that it is on the partial width of the wall, then it shall be 1/6 of the bearing width. So, for RC slab with a span exceeding 30 times the wall thickness, that is for large span slabs, whether it is bearing on full width or partial width of the wall, it shall be equal to 1/6 of the bearing width. If it is bearing on full width of the wall, then obviously that bearing width shall be equal to the wall thickness. Okay. So, we have provided you some guidelines obtained from appendix A of IS 1905, which gives you the detail about design eccentricity. However, it majorly depends on the judgment of the structural engineer. Now, once you have the eccentricity, how will it affect your design of masonry wall? For that, you have to look into table 9 of IS 1905, where it defines stress reduction factor depending on slenderness ratio and eccentricity. So, you have the slenderness ratio varying from 6 to 27. Why up to 27? We have earlier seen that the slenderness limit of masonry wall is maximum up to 27. Okay. Apart from this, the eccentricity in this table is expressed in terms of eccentricity of loading divided by the thickness of the member, that is the wall thickness. So, it has been considered to vary from 0 to 1/3. So, what you observe from this table is that you tend to account the effect of slenderness ratio and eccentricity through use of stress reduction factor, which is obtained from table 9 of IS 1905. Now, having seen the eccentricity, now let us look into a bit about lateral supports. Now, coming back to the slenderness ratio concept, we have seen that slenderness ratio can be based on effective height or it can be based on effective length. Why do you place such limits? The slenderness ratio based on effective height assures that the slenderness ratio assures that we prevent buckling under vertical load. So, a slenderness limit imposed in terms of effective height prevents buckling under vertical compression. How do you achieve this prevention of buckling under vertical load? If your slab is bearing on the wall, the minimum bearing width shall be equal to 90 millimeters. You cannot have bearing less than this. If your slab is not bearing on the wall, then you need to properly anchor the slab to the wall through non-corrodable metal ties. What is the dimension of these metal ties? These metal ties have rectangular cross section of 6 millimeters by 30 millimeters. So, these are kind of a plate or a bar, and at the end you have a Y kind of split in the bar, and this very section, as you can see, has to have a minimum length of 600 millimeters. These diagrams have been obtained from IS 1905. You can always have a look into the code, and what you observe that the length of this very connector or metal tie is 600 millimeters, and these ties should be placed at a maximum interval of 2 meters. On the other hand, the slenderness limit expressed in terms of effective length is able to resist horizontal force components to ensure stability against overturning, and in this case cross walls, piers or buttresses act as lateral supports in order to limit the slenderness based on effective length. The minimum thickness of these cross walls is half of the supported wall or 90 millimeters, whichever is larger. Also, these cross walls or pier or buttresses should have a minimum length of 1/5 of wall height. You might recall that in a previous slide on effective length, we have mentioned it to be 1/6 of wall height. Now, it depends on the consideration by the structural engineer as well, but mostly the minimum length should be 1/5 of the wall height, and these have to be built at right angles and bonded to the wall. Now, having understood this concept of slenderness limit and how do you achieve using lateral supports, now let us look into what is an adequate lateral support. For an adequate lateral support, the support should be capable of resisting the total lateral load plus 2.5% of the total vertical load. If your building is load bearing up to 4-story height, then in that case maximum height to width ratio shall be equal to 2. The stiffening cross walls are also provided as per table 2 of IS 1905. The slabs bear or are anchored to cross walls. We have seen about when do we say that the slab is bearing completely on the cross wall, when the bearing width is more than 90 millimeters. When do we say that they are anchored properly? When you use sufficient metal ties, as we have seen in the previous slide and also we can see in this very figure. So, these ties placed at spacing of not more than 2 meters. Now, the cross walls are jointly built with load bearing walls or interconnected through toothing or ties sometimes as well. Now, these toothing or ties can have these dimensions and a spacing less than 1200 millimeters as well. You can also have a look at this very table obtained from IS 1905, where based on the thickness of wall which is to be stiffened and the maximum story height, you have the information about what would be the thickness of the stiffening wall. As you can see in this very figure, this is a wall which is to be stiffened and this is the wall which is stiffening, that is, it is a stiffening wall. So, let us say that if you have a 4-story building and the thickness of this wall is, let us say, 200 millimeters, then you need 200 mm thick stiffening wall as well, and the maximum spacing of a stiffening wall shall be in that case equal to 6 meters. So, the spacing of stiffening wall shall be always lesser than 6 meter in that case. Okay. Apart from these adequate lateral supports, we should also understand for external walls of basement and plinth, we should have the minimum crushing strength of brick as 5 megapascal. This is only true for external walls in basement and plinth level. Why is it important to consider these? Because often the walls in basement and plinth level are exposed to severe environmental degradation. Why? Because there is always humidity coming from the soil. So, in that case you have the minimum crushing strength of brick to be used as 5 megapascal. The mortar has to be M1 or richer. The maximum clear height of ceiling in basement shall be 2.6 meters, and walls stiffened to prevent buckling under vertical load and overturning under lateral load. In case of soil pressure on basement walls, we will consider the traffic load, but we will not consider surcharge from adjacent building, and this traffic load shall not exceed 5 kilonewton per meter square. The basement wall has to be approximately 40 millimeter thick. The table 3 of IS 1905 gives us more detail about the minimum thickness, which in some cases may be 30 mm as well, but conservatively please consider the minimum thickness of basement wall to be 40 mm. Now, this very table, as you can see that it has given the minimum thickness of basement wall as 40. The minimum thickness of basement wall as per table 3 of IS 1905 1987 shall be conservatively taken as 40 centimeters. In this case, as you can see, this is the table 3 obtained from the code, and you can also have 30 centimeter thick basement wall in some cases, depending on what is the height of the ground above the basement floor level, etc. But conservatively, I suggest you to consider the thickness of basement wall to be always greater than or equal to 40 centimeter. Further, you can also have lateral supports coming from other walls. For example, if you have I-shaped wall configuration or a T-shaped wall configuration, you can always tell that there is some cross wall which is supporting the other, and in that case the overhanging length of load bearing wall, which effectively functions as flange to this wall, shall be equal to 12T or H by 6 in case of such I or T walls. In case of L walls or U walls like this, then the effective width of the flange shall be taken as 6T or H by 16. In this case, T is the thickness of bearing wall and capital H is the total height of wall above the considered level. Okay, so far we have seen into so in this class we have looked into various geometrical details such as effective height, effective length, effective thickness, and thereby slenderness ratios and slenderness limits on masonry walls. We have also looked into adequate lateral support, which is in form of cross wall, etc. We have also seen specifications related to that as based on IS 1905. In the upcoming class, we will further look into various design aspects of masonry walls, particularly from design loads and permissible stresses perspective. Thank you.